In this video, we're going to focus on the derivatives of trigonometric functions. There are 6 formulas that we need to be familiar with. First, let's take a look at the derivative of the sine function. Okay, so let's say we have sine of u, where u can be any function of x. Okay, and then if we differentiate with respect to x, this will give us cosine of u times du dx. Now, if you can notice, there are 2 parts in the formula. Okay, this is true for all the formulas, alright? So the first one, you can think of it as the main derivative, alright? In general, the derivative of the sine function is the cosine function, okay? And then the second one, this factor du dx, this is a result of applying the chain rule, okay? So why did we apply the chain rule? Because the argument that we used here, u, is a function of another variable, in this case x. And we are differentiating not directly with respect to u, but with respect to x. Alright, that's why we applied chain rule. This gives us a general formula. Okay, this will be the pattern for all the formulas that we will be using. Alright, so now let's look at the derivatives of the remaining trigo functions. So next, derivative of the cosine function is negative sine. Okay, derivative of the tangent function, it's secant squared. Okay, cotangent, negative cosecant squared. Derivative of the secant function, it's the product of secant and tangent functions. Alright, and lastly, the derivative of the cosecant function is negative cosecant times cotangent. Now, to help us in memorizing these formulas, we can take advantage of some patterns and similarities, okay? So if you look at the co-functions, these are the trig functions with co in its name, okay? Cosine, cotangent, and cosecant. If you look at their derivatives, they are negative, right? If you look at the first 2 formulas, they are easy to remember, right? Because they are just derivatives of each other. Again, cosine is just negative. And then if you look at tangent and its cofunction, which is cotangent, the similarity between the 2 formulas is that their derivatives are raised to the power of 2. Okay? And then lastly, if you look at secant and cosecant, both of the formulas are products of 2 trig functions. Secant tangent and then cosecant cotangent. Okay? Now let's take a look at some examples. First, we are asked to find the first derivative with respect to x of the function y equals sine 5x. Okay? So y equals sine 5x. Again, we are asked to find the first derivative with respect to x. Okay? The left-hand side of the equation, of course, this is dy dx, right? And then the right-hand side of the equation, this takes the form d dx sine of u, right? Where u is the argument 5x. Okay? And so the formula for the derivative of sine of u with respect to x takes the form cosine of u du dx. Okay? Where again u is 5x. That's why the first derivative is cosine of 5x times 5. The first part, cosine 5x, this is cosine of u, right? And then 5 here is du dx. Okay? Derivative of u with respect to x, so it's 5. Rearranging, we get 5 cosine of 5x. This is now the final answer. Problem number 2. Find dy dx if y is equal to sine cube 5x. Okay. Now, if a trig function is raised to a certain power, like in this case, sine is raised to the power of 3, we can rewrite this as quantity sine of 5x raised to the power of 3. Okay? So in this way, we can clearly see that this takes the form u raised to n. And if you can still recall, expressions in this form can be differentiated using the general power rule, right? So the derivative with respect to x of u raised to n, where n is constant and u is a function of x, is equal to n times u raised to n minus 1 du dx. Okay? Where u in this case is sine 5x. Okay? So this is u, right? And n is 3. Therefore, if we take the derivative with respect to x of our given function here, sine cube 5x, it will result to 3 sine 5x, or 3 times quantity sine 5x raised to 2 times quantity 5 cosine 5x. So 3 here, this represents n from the general power rule, right? Sine 5x again is u. Okay, here, u. N is 3. And then 2, this is the result of n minus 1. N is 3, so 3 minus 1 is 2. And then this part here, 5 cosine 5x, this is the result of taking the derivative of u with respect to x. Okay, remember that u is sine 5x. So the derivative of sine 5x with respect to x, this is equal to cosine of 5x times the derivative of 5x with respect to x. And that is equal to 5, right? So rearranging, we get 3 times 5, that's 15. So 15 sine squared of 5x cosine of 5x. That's our final answer. Next problem. Find dy dx if y is equal to x over 2 plus sine of 2x over 4. Okay. Okay, we have fractions here. So some of you might immediately apply the quotient rule, right? However, if you look at the denominators, both are just constants. Okay, so there is really no need to apply the quotient rule. We can just apply the constant multiple rule, where we factor out the constant and differentiate the rest. Okay. Now, just to be clear, let's isolate x over 2, for example. Let's make a new function, y equals x over 2. And since it's a fraction, let's apply the quotient rule. Okay. So taking the first derivative with respect to y, dy dx, or y prime, applying the quotient rule, low d high minus high d low over low squared. So low, that's the denominator, 2. D high, derivative of the numerator. So derivative of x with respect to x, that would be 1. Minus high d low, so copy the numerator x. And then d low, that's the derivative of the denominator, right? So it's just a constant. Derivative of a constant is 0 divided by the denominator squared. So 2 squared, that would be 4. Okay, so if we simplify, we get what? This will be 0, 2 times 1, that's 2, divided by 4. This will be 1/2, right? Now, if we just apply the constant multiple rule, y equals x over 2 initially, right? So if we just rearrange, factor out 1/2, so we will be left with x. Okay, so constant multiple rule, y prime is equal to, factor out the constant, right? 1/2, then differentiate. the rest of the expression. Okay, so derivative of x with respect to x, that would be 1. So y prime is 1 half. Okay, so again, this is applicable if the denominator is just a constant. Therefore, the derivative of the given function here is equal to 1 half. Okay, again, this is the derivative of x over 2 with respect to x plus, so the second term, sine 2x over 4. Again, the denominator is just a constant, so factor out 1/4 and then differentiate sine of 2x with respect to x. Okay, so the formula is cosine of the argument, so that's cosine of 2x, okay, times the derivative of the argument with respect to x. So this is 2x, the derivative of 2x with respect to x is 2, okay? And then simplifying, we get 1 half plus 1 half cosine of 2x. We can actually consider this as the final answer, or in this form. However, because of the concept of trigonometric identities, we can rewrite this expression into another form. Okay, this is actually the half angle identity of cosine squared of x. Okay, this is derived from the double angle identity of cosine 2x. So if you can still recall, or if you're familiar with the double angle identity of cosine 2x, so this has three forms. Okay, one of the forms is 2 cosine squared x minus 1, right? So if we isolate cosine squared x, what will happen is that we have to transpose -1 to the left-hand side of the equation. So it will become cosine 2x plus 1, okay? And then divide both sides by 2. So cosine squared x is equal to, so cosine 2x plus 1, right? Divided by 2, okay? So this is equivalent to, or this is the same as this one. And it's equivalent to cosine squared x, okay? So if it is required to simplify further using identities, then this should be our final answer. Next problem. Find dy dx if y is equal to 3 tangent of 2x plus tangent cubed 2x. Okay, so this is the given. So let's start with the first term. We have 3 tangent of 2x. Just leave 3 as is. Okay, according to the constant multiple rule. And then differentiate tangent of 2x with respect to x. So the derivative of tangent is secant squared. Okay, in this case, secant squared 2x. Then again, chain rule, the derivative of 2x with respect to x, that would be 2, right? So here, for the first term, okay. Then for the second term, this is again in the form u raised to n. So we apply the general power rule, right? The general power rule, n times u raised to n minus 1 du dx. In this case, u is tangent of 2x and n is 3. Okay, so we have here n is 3, then u is tangent of 2x, right? Then n minus 1, where n is 3, so 3 minus 1, that would be 2. Okay, so tangent squared of 2x. And then lastly, du dx. U is tangent of 2x, the derivative of tangent of 2x with respect to x is secant squared of 2x, and then derivative of the argument 2x is 2. Remember the chain rule, do not forget to differentiate the arguments. Okay, so let's simplify. We have here for the first term 3 times 2, that would be 6, secant squared 2x. And for the second term, we have 3 times 2, that's also 6, times tangent squared 2x, secant squared 2x. Okay, we have here GCF, common factors 6. We have also 6 on the second term, and then secant squared 2x, secant squared 2x. So factor out 6, secant squared of 2x will get 6 secant squared of 2x times the quantity 1 plus tangent squared of 2x. We can consider this as the final answer. However, if you can notice, this expression here is actually the Pythagorean identity of secant squared 2x. Okay, and so if we simplify further, this will result to 6 secant raised to the fourth power of 2x. Okay, so this is now our final answer. Next problem. Find dy dx if y is equal to cosecant x minus 1/3 cosecant cubed x. Okay, so derivative of cosecant, that's negative cosecant, in this case x, times cotangent x, minus, so we have 1/3 cosecant cubed x, apply constant multiple rule. So we have 1/3 and then general power rule for cosecant cubed of x. So bring down 3. The power will be reduced to 2. So 3 minus 1, that would be 2. So cosecant squared of x. And then differentiate cosecant of x with respect to x. So again, we have negative cosecant x times cotangent x. Now, if you're asking if we applied the chain rule, as you can see, the argument is just x, right? And the derivative of x with respect to x is just 1. Okay, so we still applied the chain rule, and the two terms are just multiplied by 1. Okay, so simplifying, we get negative cosecant x cotangent x, and then the second term, we have here negative times negative becomes positive. 1/3 times 3, so this is just 1. And then we have here cosecant squared x times cosecant x, so cosecant cubed x, and then cotangent x. Okay, do we have common factors? We have common factors, right? Cosecant x, we have here cosecant x also, and cotangent x. So factor out the common factors, cosecant x, cotangent x. We are left with -1 on the first term, and then second term we are left with cosecant squared x. Okay, and then this expression inside the parentheses, let's rearrange so that we can clearly see that it's the Pythagorean identity of cotangent squared. Okay, and so simplifying further, this will result to cosecant x cotangent cubed x. Okay, this is now our final answer. Next problem. Find dy dx if sine of x over y equals y over x. This is an implicit function, so we'll have to apply implicit differentiation, right? First, derivative of the sine function, that's the cosine function, right? So we have here cosine x over y, and then differentiate the argument with respect to x. This is in fractional form, so we have to apply quotient rule. Low d high minus high d low over low squared. So first term in the numerator, low d high, copy the denominator, and then differentiate the numerator x with respect to x. So that would be 1. Y times 1, that's y. Okay. Minus the second term, high d low. So copy the numerator x, and then derivative of the denominator y with respect to x. So we have here y prime, okay? And then divided by low squared, or the denominator squared. So y squared equals, so the same formula, quotient rule, low d high minus high d low over low squared. Now our goal is to find dy dx, right? it's the same as y prime. So what we need to do from here is that we have to isolate y prime, right? Isolating y prime, first we can perform cross multiplication to eliminate the fractions. Okay, so cross multiply x squared to the left hand side of the equation, and then cross multiply y squared to the right hand side of the equation. Okay, so this will be the result. Okay, and then next we distribute. So distribute x squared cosine x over y to the expression here inside the parentheses. Also distribute y squared to xy prime minus y. Okay, so this will be the result. Now from here we can isolate all the terms that contain y prime. So this term and this term. Okay, so we have here on the left hand side of the equation all the terms that contain y prime. Okay, and then next we factor out common factors. For the right hand side of the equation, we have here y, so we can factor out y. Okay, and then left hand side of the equation, we have y prime, and also x. Okay, so factoring, we get this equation. And now to isolate y prime, okay, divide both sides of the equation by x and this expression here, right? So as you can see, we have here uh, the same expressions, right? y squared also in the denominator, and then x squared times cosine x over y, x squared times cosine x over y. So we can cancel out this expression, okay? So that we are left with y over x, and this is now our final answer. Next problem, find dy dx if x is equal to sine squared y minus cosine of 2y. Okay, the equation given is in the form x as a function of y. And since we are asked to find dy dx, we can use the inverse function rule of differentiation. We can also use implicit differentiation, but let's use inverse function rule for this problem. Okay, given x equals sine squared y minus cosine of 2y, first we have to differentiate with respect to y. Okay, so this will give us dx dy equals, so sine squared y with respect to y, or the derivative of sine squared y with respect to y, applying general power rule. So bring down 2, we have here 2, and then sine y, and derivative of sine y with respect to y, that would be cosine y. Okay, minus derivative of cosine 2y with respect to y, so cosine negative sine, and then derivative of 2y with respect to y, that would be 2. Okay, so simplifying, you get 2 sine y cosine of y plus 2 sine 2y. Now if you look at the first term, we have 2 sine y cosine y. This is the double angle identity of sine 2y. Okay, so this will give us sine 2y, again from the double angle identity, plus the second term 2 sine 2y. So we have similar terms. This will give us 3 sine 2y. Then remember, this is dx dy. What we want is dy dx. So let's take the reciprocal of this equation. We'll get dy dx equals 1 over 3 sine 2y. We can stop here, or we can apply identity because we have 1 over sine 2y and it's equivalent to cosecant 2y. So we can rewrite the final answer as 1/3 cosecant 2y.